So there is this belief that attention is actually all you need. It's a very good model, but it has its own shortcomings. One of them is you're going to have a quadratic cost to compute these multi-head attentions in terms of the sequence length. So if your input sentence is really long, then this is going to take a lot of time to be computed. The other one is when it comes to inference, you're going to output one word at a time. Initially, you're going to be fine. Your multi-head attention here or the other one here are going to have a lower cost. But as you keep outputting more and more words, it's going to become costly and more costly because the cost of this guy, masked multi-head attention, is quadratic in the sequence length. And we're going to go through 3 papers trying to address that problem, trying to address the problem of having quadratic cost. This is an assignment for you to watch this video. So I'm going to go through this one really quick. And the next 2 ones, we are going to spend a little bit more time on them. I'm going to give you an overview, and then you can ask your questions. We have the attention mechanism. This is actually how you're going to implement it on your computers. You're going to take the input sentence, which is a matrix. You're going to multiply it by 3 other matrices to give you query key value. We usually process things in mini batches when it comes to deep learning because it's going to enable you to do parallel processing and use your GPUs more efficiently. There is going to be a batch size, there is going to be a sequence length, and there is going to be the dimension of your query key and values. Then you can multiply. You need to multiply Q by K. And the cost of that, in terms of computational cost, is going to end up being order L times D. And the memory footprint is actually storing this matrix, which is going to also be quadratic in L. You need to store it because you're going to do some computations on it. And then when it comes to backward pass, you also need that when you're actually computing your gradients. We usually have 512 for the sequence length when it comes to language modeling. But if you go the character level route or byte level route, then easily a sentence could end up having these many characters in it. So this could end up being really long. And what is the problem with that? If you have a sentence that is this long, you're gonna store every single entry of this matrix. That's gonna be 64,000 times 64,000 times each one of them is a float 32 number, and that's gonna require 16 gigabytes of memory. And our GPUs usually have 2x or 3 times more memory than that. But this is only for one layer, just for one of these operations. Imagine stacking multiple of them on top of each other. That's why usually when it comes to language, your batches are in the order of 4 or 32 or something like that, because you're gonna run out of memory on your GPUs. To deal with the memory problem, you can actually expand attention and write it in terms of individual terms. Maybe you're interested in the individual query. So let's go query by query and then compute the attention, spread it among the keys. This exponential, in addition to this negative z sign, is actually going to give you your softmax. So whatever term that you have in your denominator, you can take its log and then put it within this exponential. So this z is actually log of the summation of a bunch of exponentials. And then you're going to have unidirectional attention. This is when you use it for decoder. This is how you're going to end up with having to store smaller matrices. And basically, you're reducing the cost of storing it to order L versus order L squared. The other idea is locality sensitive hashing idea. What is the idea here? The big idea, the big observation, is that the softmax is usually dominated by its largest elements. So as soon as a query and a key are very similar to each other, they are going to dominate your softmax values. And the ones that are less similar are going to be very close to 0. Basically, you can ignore them. Based on that idea, you can say that I'm going to look at only the keys that are the most similar to my queue. And how do you do it? Any two vectors that are very similar to each other, we can just put them in a single bucket. And the ones that are dissimilar, they're going to have different buckets. And then you're going to keep only a few buckets, maybe 2, 8, or 16. And in this formula, the only thing that you need to change is do your summation still from time 0 up until the current time, but then do your summation only over the keys, over the keys that have the same or are in the same bucket as your queue. And this way you're actually reducing your cost, computational cost. So one of them was about computational cost. The other one was about memory. There is also another trick. This is a very useful trick to know about. It's not only about transformers, but about other models. Usually when you go from one layer to the next layer of a neural network, you need to store these matrices. Why? Because when you're actually computing your gradients, you need these. And that's actually the beauty of backpropagation. Backpropagation is not only about chain rule, but also about memoization. So you're gonna memorize or store or cache some of these values because later on you're gonna need them. And this way you need to store them in memory. You need to store them somewhere. But it would be good if you can actually compute them whenever you need them. And this way you are trading off memory for compute. And there is this trick that you can actually do it. It's called backpropagation without storing activations. You're going to divide your X into two components, and you can do it channel-wise. You do your attention over one of the channels, and then you do your feed-forward component over the other channel. Why is it useful? Because now that you have this nice formula, y1 is equal to x1 plus f of x2, y2 x2 plus g of y1. You don't need to store y1 and x2 anymore. You can just compute them whenever you need them. And whenever you're going backward, you know y1 and y2. And from those two, you can actually compute x1 and x2. You don't need to keep them in memory anymore. The other trick is if your sequence is very long, just process it in chunks. And we also use this idea a lot when it comes to images. If an image is really high resolution, like satellite images, you don't process the entire thing at once. You're going to process it in patches. You do the same thing here. There is also another observation that you can actually save some parameters when you are creating your query key and value. You are multiplying your input by three matrices, WQ, WK, and WV. The idea is that WQ and WK could actually be the same thing. And therefore, query and key are living in the same space. And this way, you are sharing parameters. You're dividing the number of parameters that you need actually for representing K and Q by half. Now the question is, after doing all of these, did you lose anything or how much did you lose? And it turns out that you didn't lose much. This reversible trick is actually a good trick to use. You don't lose much. The other one is in terms of perplexity, having shared Q and K weights is going to give you the same performance, at least for these benchmarks that they were covering. And one of the benchmarks is ENVK8. The other one is ImageNet 64. So what I want you to do is explore these two datasets. These have nothing to do with translation. These have nothing to do with language modeling. These are just some benchmarks to test the performance of this method. Did you really manage to make things more efficient? And the locality sensitive hashing idea, you're going to lose something if you have very few hashes or hash buckets. Otherwise, you're not going to lose much. And the metric here is perplexity. And perplexity is the geometric average of 1 over your probabilities. Once you have a sentence, the role of language modeling is to actually associate the probability to that sentence and how likely that sentence is. When you want to validate whether you did the correct thing or no, in terms of your evaluation metrics, you're going to use perplexity, which is root n. N is the length of your sequence. If you take a log, that's going to give you 1 over n of the negative of the log of your probabilities, which is just the average. One of them is arithmetic averaging, the other one is geometric averaging. And they're equivalent. They're different by a log. Any questions about reformer? Was everything clear? Cool.